Hello everyone, I'm Rifeng Wang from UConn Dr. Burgess Lab. I am a fifth-year PhD student. The topic of my presentation is understanding macrosphere in vitro drug release through imaging-based analytics. As known to us, PLG is the most popular bioresorbable material and it became the reference material for many therapeutic products, such as sutures, grafts, implants, as well as parenteral injectable macrospheres. The red table shows the current commercial PLG macrospheres products launched on the US market. Up to now, more than 10 macrosphere products have been approved by FDA for clinical use. One example is Arrestin, which was selected as a reference listed drug in this present study. Arrestin is a sublingual controlled release product containing the minocycline hydrochloride, which is incorporated into PLGA. For complex drug products such as PLG-based drug products, the FDA requires the generic product should contain the same active and inactive ingredients in the same dosage form and concentration as the LD. However, for complex drug products, Q1, Q2 similarity is not always sufficient. The Q3 similarity must also be considered. The arrangement of matter can also affect the drug product performance. The left picture here shows the typical internal macrostructure of a macrosphere, where the drug and the pores are distributed in the polymer matrix. A better understanding of the macrostructure properties that impact the drug release mechanism will contribute to a more comprehensive evaluation of product performance and function. However, the intrinsically small size and the complexity of macrospheres challenges the resolution and the effectiveness of conventional calculation methods. Focused beam scanning electron microscopy is a new generation electron microscopy imaging platform that supports internal macrostructure imaging with high resolution. Compared to the conventional mechanical sectioning technique, FIB-SEM can visualize the cross-section surface with macrostructure details accurately maintained. The collected images can be processed and segmented into different material phases by software as shown in the red figure. Then, through repeated FIB milling and subsequent SEM imaging, a 3D internal structure can be reconstructed. This allows for direct macrostructure quantification for all visible phases. In this project, we select Arrestin as a reference listed drug, and the specific M1 is the preparation and the calculation, as well as in vitro release testing of compositionally equivalent minocycline hydrochloride macrospheres. Next is the calculation and analysis of the macrostructure of prepared macrosphere using FIB-SEM. According to the patent of Arrestin, it was manufactured using coactivation method. The API used for manufacturing is macronized minocycline hydrochloride. The commercial PLG, Rhythm RG503H, which has similar properties to the polymer in the RLD, was used for preparation of all the in-house formulations. The right schematic here shows the preparation of macrospheres using in-house designed glass vessel assembly for coactivation process. The parameters like stirring speed, silicone oil viscosity could be changed to prepare different macrosphere formulations, as the left table shows. The table here shows the drug loadings of the formulation A to D. They are all close to the RLD, around 27%. The size distribution results indicated on the formulation A and C have larger particle size than B and D. The main reason could be the high viscosity of silicone oil supports smaller droplets to exist in the coactivation step, and also prevents the small droplets from merging to a large droplet. As the right picture here, the formulation A to D, they have similar appearance to the RLD, which is a well-dispersed yellow powder of minocycline hydrochloride macrospheres. Here shows the SEM results of in-house formulations. They have similar morphology with dense and relatively smooth surface. Before the in vitro study, the stability test of API was conducted. The results indicated that the drug solution with a lower concentration showed a relatively better stability than higher concentration. Considering the stability issue, the in vitro release study was performed using sample and separate method, as the top right schematic shows, and do media replacements in every sampling time point to decrease the impact of the API degradation. A reproducibility test was performed using the same batch of formulation A. Their release profiles can be basically overlapped. So current in vitro release testing method has a good reproducibility. At the release profile shown here, the compositionally equivalent microspheres formulation A to D, they have different release behaviors. Interestingly, formulation A and C have similar large particle size, but their release profiles are quite different, which may be due to the different microstructure, which will be discussed in the following slides. The release profile of all the four formulations showed a good fit with first-order model. A group of pictures on the right show the state of the microspheres during the initial release testing. Pictures were taken after the tube was centrifuged at a sampling time point. We can see that microspheres gradually swelled over time. Also, the microspheres turn dark at the end stage of the release profile, and the darkness is the color of the drug degradation products, which indicates that the drug degradation may still occur inside the microspheres. Since the darkness at the end stage is different among the four formations, it is suggested that the darkness might have a relationship with the release characteristics. Then we used ImageJ to analyze the gray value of the microsphere's concentrated area in the image. We found that the gray value showed a linear correlation with the release constant from the first-order model fitting for all the in-house formulations. In other words, the formulation with a slow release rate could trap more degradation products in the microspheres, giving them a darker color. As aforementioned, through repeated film milling and subsequent SEM imaging, a 3D internal structure can be reconstructed by software using an artificial intelligence algorithm. A 3D digitally transformed microsphere, as the red picture shows, allows for direct 3D microstructure quantification, including volume, fraction, size distribution, especially the spatial distribution of polymer, drug, and pores. From the cumulative polymer distribution from surface to center, we found that the polymer content in 35% outer layer is correlated to the release constant from first-order model fitting for in-house formulations. The more polymer content in the outer layer, the lower release rates. This finding answers the previous question. Formulations A and C have similar particle size but different polymer spatial distribution, leads to different release profiles. Interestingly, we also found that some hollow particles in the in vitro degradation samples on day 6. Moreover, the thickness of the polymer shell is roughly 35% of the radius. This confirms the important role of the outer polymer layer in the release. The residual PLG shell may act as a diffusion control layer, which indicates that the drug release from the minocycline hydrochloride microsphere may be controlled by the diffusion mechanism. This hollow particle phenomenon can be explained by the heterogeneous erosion of the polymer. For PLG microspheres, it is typically bulk erosion. The PLG will be degraded to lactic acid and glycolic acid by hydrolyzation. Moreover, an accumulation of the degradation products in the center can lead to a significant drop in the local pH and subsequently accelerates the polymer heterogeneous degradation, which results in the center polymer depletion first, thus leave a hollow particle. Combined with the gray value analysis above, the formulation with slow release rate could trap more drug degradation products in the microsphere, giving them a darker color and vice versa. To summarize, microstructural properties, especially the spatial distribution of polymer for in-house formulations as determined using the FibSEM, was identified as an important characteristic affecting the release performance, which provides a novel perspective to understand the release mechanism. A hollow appearance developed during the in vitro release for minocycline hydrochloride microspheres, which may be due to an autocatalytic effect resulting in the accelerated heterogeneous degradation of PLG. Correlation between internal phase spatial distribution and the in vitro release characteristics can potentially provide a more comprehensive understanding of the impact of microstructure properties on the underlying release mechanisms of the microspheres and aid in the establishment of Q3 equivalence. Thank you.